Yeah, no, it's... yeah, so I have a backup slide about that. Yeah, so the outflow is continuing to expand, so it should be resolvable with VLBI sometime within the next few years, possibly as long as within a few decades. So we do hope to look at it with VLBI, and it might start to be resolvable soon, but as far as I know, they haven't managed to resolve it yet. So, but yes, as this handy backup slide shows, the radio emission is still bright enough that we hope to be able to continue observing it for a very, very long time. So.
Did you say the X-ray was there? Does anyone know, or do you know if there was any burst data?
Yeah, I think there was just a ROSAT limit, which was...
What's the ROSAT limit?
Yeah, I don't think there is anything. It seemed to me reading this paper that they were surprised to see this here. So yeah, it'll be interesting. As I mentioned, our group has upcoming Chandra observations, and I know other people are presumably going to keep looking at this in the X-rays. So it will be interesting to see what happens.
The X-ray spectrum early on was very distinctively hard. Are you interested? Is there any change in spectral shape after the drop?
I'd have to go back and read this paper in more detail, but that would be a very interesting question, yeah.
Yeah, it's not clearly correlated with bright states going one direction, faint states go the other. I can't remember exactly what. But it's definitely not constant over the full rest of the other. Pardon?
Are there any
We haven't seen that in the radio, no. Oh, optical spectra. So, so as far as I know, there was no optical detection of the source initially, and as far as I know, I don't think anyone has detected lines at late times. You can maybe correct me if I'm wrong.
Okay, let's move on. Next paper is data. So from radio detection over candidate to the first radio observations of the optical selected. Is this going to
Oh no, this is I'm completely changing my persona by putting on this T-shirt here, just in case you forget which talk I am giving.
Okay. Now it's a TD shirt. Okay.
Yes. Now it's a TD shirt. Let's see. Did that mess up the? That might have messed up the microphone. No? There we go.
Okay. So the first radio detection of the multiply selected TD candidate. Are these also candidates, or are these all candidates? Okay. Okay.
All right. So I think everyone is convinced that Assassin 14 Li is a very good candidate, but we can call it a candidate nonetheless. So we've all been at this workshop all week. So again, I will just go through this background material very quickly, but as all of you know, most TDEs are discovered at optical UV and X-ray wavelengths, and it's seeming increasingly likely that most TDEs do not produce jets. And we have detected these 2 events in the radio, and there's these possible very late time detections of a couple of other X-ray events, but for the most part, the detailed radio observations that have been possible until this year were just of these highly relativistic, unusual events. However, we do expect, although again we can argue about the details, we do expect that most TDEs will have a period of super Eddington fallback and likely a period of super Eddington accretion. And so therefore, it is natural to expect some kind of outflow. So this is just one particular simulations paper, but we saw the simulations this morning. We've seen them throughout the conference. This one just shows that for a variety of impact parameters, you do have a period of several months where you expect this rate to be super Eddington. And however, a lot of the observations that we've seen in the optical do not directly provide support for these outflows. We do see these, we do see these broad spectral features, but the velocities are low. In the X-ray spectra, we see very narrow velocity lines for assassin 14 Li. So the observational evidence for these type of outflows expected from super Eddington accretion, I would argue, has been lacking for the bulk of the TDE population. So enter assassin 14 Li. Again, we've heard several very nice talks about this already, but it is special because it is very nearby. I think it's the nearest published TDE that has been detected within the past 10 years or so. This is the very nice spectral energy distribution evolution from assassin. And the X-ray, UV, and optical observations considered on their own very clearly indicate that this is a TDE. It does not evolve like you would expect for a supernova or for an AGN that just is undergoing some unusual flare. So our group has been doing work searching for radio emission from nearby TDEs, and so we requested time and got time to observe this object starting shortly after it was discovered. So our first epoch was in December. We have now observed it at 6 different times with the VLA at a wide range of frequencies spanning 1.4 gigahertz all the way up to 24.5 gigahertz. And to fully understand what's going on in the radio with this object, we also note that there are 2 archival detections of this source at 1.4 gigahertz, around 3 millijanskis each. These were about 15 years before the TDE. So this is a fairly significant flux compared to the flux we see. It's actually higher than the flux we see at 1.4 gigahertz for the duration of the flare. So it's important to consider what impact these archival, or what these archival radio observations imply about the emission that we're seeing. So again, you saw this plot previously in a SOFS talk, but this is our radio observations of assassin 14 Li. So if these green points are our first epoch of data, and then the peak of the spectral energy distribution evolves from high frequencies to low frequencies over these 9 months of observations. You can see that the source has faded significantly at high frequencies, but is still very bright at around 1.4 gigahertz. This plot on the left shows the total flux we've observed. This dashed line here is a model for an underlying quiescent component. Since we have these archival radio detections, we're forced to infer that there was presumably some low level of HEN activity in the galaxy before the tidal disruption event happened. The radio emission is clearly not due to star formation because we have a archival optical spectrum of the galaxy from SDSS. There's no evidence for any sort of star formation in this galaxy. It seems very likely that this nuclear source in the other surveys is associated with some kind of AGN. So we just have a simple model here, and then we subtract that off of the fluxes to get this transient component of the emission on the right. And again, it doesn't really qualitatively change the behavior. We still see that the peak is moving to low frequencies over time, and eventually we expect it to relax back to something that looks like this underlying quiescent component. So we fit the data with our standard synchrotron equipartition model. I refer people to this very nice explanation of that model and how it applies to both relativistic and non-relativistic sources if you want to see the full details and all the math. But basically all we need is to fit the shape of the spectral energy distribution, extract out the peak flux and the peak frequency, and then we can use that to infer very nice properties of the outflow as it evolves over time. These fits are all done separately, epoch by epoch, so we don't make any assumptions necessarily about how the outflow is evolving in time. We just have these nice independent snapshots. So this is, for example, how the size of the emitting region evolves with time in the radio. So there's a number of lines on this plot, so I'll just step through what they all mean. The solid lines are the best fit to just the transient component, so the right panel in the plot of the fluxes that I showed 2 slides ago. The dashed lines are if we just assume that, well, maybe this quiescent component doesn't really exist, and we just try to fit the model to the total flux. So I'll note that qualitatively this doesn't change our overall conclusions from the radio emission, but the 2-component model is a much better fit. And then the 2 different colors show different assumptions about the outflow geometry. So the simplest model is just to assume that we're seeing a spherical outflow, but as we've seen with very nice simulations, that's not necessarily the case. We might expect to see more of a zebra geometry where you have this kind of cone of outflowing emissions. So this one, the blue here is assuming we have some kind of conical outflow with a covering fraction of 10%. So the truth may be somewhere in the middle, but these are kind of a range of values you could estimate. We can also take the, since this is how the radius is evolving as a function of time and it's increasing at a fairly constant velocity, we can just extrapolate backward to 0 to figure out roughly when the outflow was launched. We find it was launched around August 2014. I'll come back to that in a few minutes. Next thing I wanted to talk about was our estimate of the outflow energy. So we find that the energy we get is fairly robust to the geometry. So it doesn't really matter what geometry we assume for the outflow. We recover that the energy is about 10 to the 48 ergs, which is lower than the bolometric luminosity inferred from the X-ray by quite a bit, but that's okay, as we'll talk about. This energy estimate, as was commented earlier this morning, it does depend on what fraction of the energy is in the electrons. So when we were doing our modeling of the radio emission as synchrotron emission, what we're actually observing is this synchrotron emission from the electrons. So to convert to the total kinetic energy of the outflow, which also has things like protons in it, which in fact denominate the kinetic energy, one has to assume that there is a fraction of, say, 10% in the electrons. So this has been observationally shown to be correct for relativistic outflows, but this is a non-relativistic outflow. There's some indications it may be lower. So if it were 1% instead of 10%, then you would increase the energy to maybe up to 10 to the 49. But it's still quite low. So then this is figure 2 in our paper, which just shows several other properties of the outflow. You can get the velocity as a function of time. It's fairly constant, so the outflow has not decelerated. It's still moving outward at a constant velocity. You can take the velocity and the kinetic energy and infer what the mass of the outflow is. So we find that it's a fairly small mass, about 10 to the minus 4 to maybe up to 10 to the minus 3 solar masses. You can infer the density profile, just as we did for the SWIFT event. As was mentioned this morning, this seems to be rather low compared to theoretical and other observational estimates. And this may indeed be a lower limit when you look at the normalization, but the profile that we get, r to the minus 2.6, is robust to these, to what we assume about the geometry and so on. So this is a fairly steep profile, but as was mentioned this morning, if you have a zebra-like model, it's not unheard of. And then this just shows how the magnetic field strength evolves with radius. Sorry? No? Well, you have the same amount of material outflowing, and it just hasn't slowed down yet.
But if you have something moving at constant speed, the constant rotation, and you have the same mass flux everywhere, the densities are -2.
So this is the density that was pre-existing, not the density of the outflow itself. Sorry, I did not make that clear. So what this is probing, since it's the interaction of the outflow with the pre-existing medium, we're actually, what we're observing is the total number of electrons that were accelerated into this distribution. So yeah, it's not the density of the outflow itself. So we can also, so we want to know where is this outflow coming from. So we look at we can look at the timing of when the outflow was launched and compare it to this the timing of a super Eddington accretion period for this object. So these two plots were done by James, who's one of our co-authors on our paper, and he did a completely independent modeling using his code of the X-ray, optical, and UV data. And so these are a set of simulations generated using a Monte Carlo technique. This histogram shows, for his ensemble of simulations for this TDE, when the onset of super Eddington fallback was, when the peak fallback rate happened, and then the not shown on here is the time of super Eddington, when the time of super Eddington fallback ended, which was right around the time of the event's discovery. So our estimated timing for the launch of the radio outflow agrees pretty well with this timing for the onset of potentially super Eddington accretion for this event. So this is suggestive that this outflow was associated with this period of super Eddington accretion rather than, say, being emission from the unbound tidal debris that would have been launched several months earlier when the star was actually disrupted before this material had time to fall back. We can also compute how much mass has fallen back onto the black hole during this period of super Eddington accretion, and we find, based on James's modeling, that it's about 0.02 solar masses with quite a bit of scatter. So as you recall from the previous slide, I said that our inferred mass for the outflow was about 10 to the minus 4 to 10 to the minus 3 solar masses. So this is maybe a few percent, possibly up to almost 10% of the mass that is accreted onto the black hole during this time. So there have been various simulations of what you would expect for the fraction of material blown outward in a wind during super Eddington accretion, and this seems fairly consistent with that work. This plot goes back to the density profile, and I have just plotted it in context with several other black holes for which we have well-studied density profiles. This is the radius normalized by the Schwarzschild radius of the respective black hole and the inferred density. So here is Assassin 14 Li down here with their steep and low density profile. This is M87. This is the Swift event, and this is the Milky Way. So we are, once you normalize it in terms of the Schwarzschild radius, we are probing closer to the center of the black hole than others have managed to probe before. But it is interesting that, with the possible exception of whether you trust this Swift point here, we are seeing a steeper profile than has been previously observed. This slide shows the kinetic energy of the outflow versus the velocity of the outflow as inferred from the radio emission for the 3 TDEs for which we now have radio detections. So this is the Swift event, this is the second Swift event, and then this is Assassin 14 Li, where this is the range of velocities implied by choosing the different geometries. And then, just as for illustration purposes, the stars in the background show the sample of type 1bc supernovae and gamma ray bursts and the corresponding kinetic energies and velocities of those outflows inferred. So I'm not trying to necessarily imply that the same processes are at work here, but it is an interesting analogy to draw that gamma ray bursts are a small fraction of the total population of type 1bc supernovae. So there's this small fraction of highly relativistic events that produce jets in this part of the diagram. And now, for the first time, we have a TDE in this lower part of the diagram. so which may be representative of the bulk TDE population, just as these supernovae with non-relativistic outflows are representative of that, of the bulk of that population. So this is the figure I showed in the last talk, now with the Assassin 14 Li points added on it in terms of luminosity. So this plot may now be out of date because depending on how far away Assassin 15 Li turns out to be, it may have a luminosity upper limit that is down below these data points, but the purpose of this plot is just to illustrate that many of the other TDE candidates that have been observed previously could have had radio emission at the level we see in Assassin 14 Li, and we just wouldn't have been expected to detect it because those events were further away. This object showed, I think it was 10 to the 43 in the X-ray. The X-ray falls off slightly for this object. I think it was down to, Tom can probably answer this better than I can, 10 to the 43 still, maybe 10 to the 42.
So the radio is 10 to the minus 11.
Oh, so that was the, yeah, that's right. It is very small, yes. And like I said, this is kind of a lower limit based on what you assume about the equipartition fraction. But even so, you can only push it up maybe one more order of magnitude. So it's fairly small.
The direct radio luminosity or the inferred energy?
Sorry, that's the inferred energy. This is the radio luminosity.
Yeah,
you're right.
So there are no assumptions.
Yeah. The only assumption here is this is an isotropic equivalent luminosity. So these are all assuming the emission were spherical. This is what you would get. So we know for the Swift event that it's not spherical, but just for comparing apples to apples, we plotted that on here. So that's about all I've got. I will leave my conclusions up here. It's exciting that we have detected a non-relativistic outflow in the radio, and we might expect to see more of these if we are lucky enough to find other nearby events, or if we wait until the SKA comes online and can search a larger volume for luminosity such as this. And it'll be interesting to see if we get more events like Assassin 15 OI, which may question this paradigm we're suggesting where many TDEs produce these non-relativistic outflows. Thanks.
In the optical, it's very similar to 14 and 9. I think the temperature is higher though, right? So the bolometric luminosity might be higher.
So is when you've calculated the luminosity so far, which redshift have you assumed? Because you said
for
that
15 OI?
Yeah, for 15 OI. Okay.
Yeah.
Well, there's the initial ATEL on this object has a lower redshift than is the actual correct one. So.
The correct redshift brought it actually back up to be similar to 14 OI.
And am I understanding correctly that the upper limit on 15 OI are stricter than the one on 14 OI? They're lower in the diagram?
Yes, that's
So-
in a SAP plot.
Yeah, but his plot was in terms of the flux, so I'm not.
What's the reason why it's cheaper? Does this update them further away?
Yeah, so your plot was in terms of fluxes. I'd be interested. I'd be interested to see what it looks like when you do the luminosity correction.
How long do you have to wait before you can actually see it?
So we're going to keep monitoring it, and we will find out. We have another observation coming up in November, and then we're waiting to find out whether we've been given time to keep looking at it next year. But in this case, since there is this underlying pre-existing archival radio emission, which is fairly which is not something we've seen in other events, although again, they're further away, so we might not have detected it if it was there. It'll be interesting to see. We sort of expect it'll eventually relax back to some kind of quiescent underlying steady state component. And we've assumed that this quiescent component is making a fairly significant contribution at 1.4 gigahertz. So it will be, if it fades away entirely, we will have to rethink slightly. But it shouldn't change the overall conclusion that this is a non-relativistic outflow.
This event has been behind the sun for a few months, and just in 2 weeks it's coming back.
Yeah, so it's actually an advantage of observing in the radios. We've been able to take observations all summer, no problem. So.
Yes.
Can you please second where does the estimation of velocity come from?
Right, so we do the estimation of velocity in 2 ways. One way is you can just basically take the derivative of this radius estimate, and then we find that there is a constant velocity. What we do to get this plot here is once we've determined from how the radius is growing approximately what the age of the outflow is we just divide the radius by the age. And so that's why this is the average expansion velocity here. But yeah, it's fairly straightforward, and it worked out to be, the math is very simple since it is expanding at a constant velocity.
So I have a question about the density normalization.
Yes.
This might be more of a question for James since he did the modeling, but so in the paper you get a maximum density of 0.6 per cc at 0.01 parsec. So if you extrapolate that out to the area where Alexei and where Alexei presented our predictions.
Yeah, it's way down here.
Yeah, that's like, if you use R to the minus 2.6, that's like 3 orders of magnitude below our bare minimum density. So what parameters of the fit could you change to bring that normalization up, or are you forced to conclude that the density in this AGN is dramatically less than any?
So I'm not sure if, so I'd have to run the numbers to see if we could bring it all the way up. But as you can see, just from this plot, it depends a little bit on the geometry you assume. So if it's not a spherical outflow, the normalization goes up, but that won't, that alone doesn't help completely. Another thing that might help is, again, our assumption about what fraction of the energy is in the electrons. So if the energy comes up, then the density should also come up. So I'd have to run the numbers to see whether that would fully bring it up. But another suggestion is that we do have this evidence that there may be this weak AGN activity. So it's possible that the portion of the density profile that we're looking at has been previously evacuated by some kind of jet in the past. So that could also explain why it's on the lower end of the densities you infer.
I think it's 300.
We expect also to have the ongoing debris.
Yes.
The ongoing debris, first we have about this velocity, about 10,000 kilometers per second. This is just the typical parameter.
So I calculated that the time of disruption.
Can I finish the question?
That was the question.
What happens to it? Why don't you see?
So the amount of luminosity that you get out of the unbound debris running into the ambient medium is very, very low.
Why?
Its opening angle is very, very small. It's confined to a very tiny, thin screen that doesn't actually intercept very much. It can actually travel for parsecs before it begins to slow down significantly. When I calculated the amount of energy that you can get out of the unbound debris, it's quite a bit smaller than what you're getting out of this outflow. It's presumably
Right.
4 or 5 coverage fraction.
Yeah, no, I did this calculation too, and if you you need a large covering angle to reproduce the energy. Another thing we considered was whether this was some kind of very narrowly beamed ultra-relativistic jet. And if you want to explain this with an ultra-relativistic jet, even to get gamma to be greater than 1, you have to assume that it has an opening angle of something like 0.5 degrees. It's really, really unphysically small. So it's the fact that you don't have this large covering angle.
Partially, even if it wasn't self-gravitating, it still covers a fairly small range of solid angles, even in like say Ming-Survey band model, that still is significant
Yeah, and then the other argument was just that the timing works out very well with the super Eddington accretion phase, and the unbound debris would have been launched presumably several months earlier, since it takes time for the material to fall back and start accreting. And so then why wouldn't we have seen radio emission? You know, we wouldn't have expected the evolution to look different.
Outflow velocity basically follows from modeling the SUV and the epoch, right? But you have basically three parameters, like the luminosity and the turnover. But this panel shows six outcomes, and presumably you will have at least the density, the radius, and the energy at each epoch that you need to fit for, right? So what relation ties these together? What assumption is underlying here?
Well, it's this assumption of equipartition. So we assume that there's an equal amount of energy in the magnetic fields as in the electrons. So then you only have the two free parameters are the radius and the energy. And then you can solve for the others. Yeah, so I refer you to the Varniol-Duran paper. They go through all of the math, and it's very nicely laid out, and shows you can solve for this in a self-consistent manner.
Right, so the change in velocity would need to change the particular parameter as a function of time?
No, if the velocity, if the velocity were changing, you would, since you're fitting each epoch independently and you're not making any assumption about how it changes from one to the next, you could be able to see that the velocity was changing. So, for example, in our model where we're trying to fit this with the total flux, you do see that the velocity would go up if you believe this model. So this is hard to explain physically. It's hard to understand why it would be accelerating, but it shows that the method would work even for a non-constant velocity.
Yeah, just a small one. What would the burden for the contour the dark and nice 2.6?
That's for that is for both of the solid lines. So that's for our transient one. The slope is not dependent on the geometry. It's the same for both. If you fit the total flux, that is r to the -2 approximately, the dashed lines.
Just a couple of comments. So regarding the assumption, so you said you assume equipartition, but on top of that you assume the value of epsilon.
Right. Yeah.
Another parameter. And you mentioned that, well, you may know epsilon pretty well. It should be roughly about 0.1, which is usually what is used to get as well.
Yeah.
Epsilon b as measured in a handful of cases, and it's actually has a wide range of including 0.1, but also very low values.
Right. Exactly.
The -4, that I guess will push up the alternative densities up.
Yeah, so the way this analysis is done, the two are forced to be equal. So yeah, that is another constraint. And as I said, there's all these systems for which we typically assume epsilon e is 0.1, or a lot of them are relativistic systems, and there's some evidence that even epsilon e is a bit lower for non-relativistic systems.
And if most cities or thermal communities are equally this kind of emission, might be a bit disappointing because the rotational radius for those is basically this is like keeping it, right? So it will be the current difficulty about 200 megaparsec. So we need the sampling model to try and find 1 year by
As close as this one or closer?
Yes. Well, in the past it was worse, right? You used to start keeping over 10 and 20 megaparsec per moment. Now we can set it up to 200 megaparsec. And last question is about the underlying component. So, how robust are the estimates using this assumption on spectral shape of the underlying component? Because we have only one sample.
Right. Yeah. So as you correctly infer, it's somewhat ad hoc. We do so to fit some of our most epochs where we have the most complete spectral coverage, we find that we do need a fairly significant contribution at the lower frequencies from the quiescent component. And then the slope is somewhat constrained by the fading at the high frequencies. So you know, if we want this significant contribution at the low frequencies, then it has to be a certain steepness. So we do the proportionality is nu to the -1, which is fairly steep for an AGN, but not unheard of for an AGN. There are the range seems to be about 0 to -1, and most are around -0.5 to -0.7, depending on exactly what the properties of the system are. So, so yes, this is a fairly simplistic model, and the slope was only limited really by the fading we see at our highest frequencies, and by the fact that if we wanted it to be any shallower than that, then it starts not really making sense to add it at all, because it's not, you're not getting a significant contribution anywhere. So.
The equation comes from the AGN outflow.
Right, right. So we're, presumably there was some sort of accretion disk there already, perhaps.
Right.
And
So then when we got the nature paper and got all these absorption circuits, is that for the AGN?
it could be, yeah.
You mean the X-ray?
Well, that could be from the, any accretion disk that was there before that's all bound to the AGN, yeah.
Is there any sign that the quiescent source is offset from the center, or are they right on top of each other?
Well, the resolution, the beam size of the archival detections is unfortunately very large. So I forget whether I left that in this slide. I don't think so, but it's 3 arc seconds or 5 arc seconds or something. It's pretty big. So as far as we can tell, it's coincident with the nucleus, but the reason we considered star formation is the beam covers a lot of the galaxy. So.
I think we should continue the discussion over coffee. So let's take a break and meet back at 4.
Thank you.
Sorry.
Don't want to run off with this. Thank you.
I don't have a right back, so
Oh, actually. Good luck.
Yeah.
אני אמרתי לך שאני הולך לקחת ככה וככה זמן, ועמדתי בזמנים שאמרתי. זה מחר, אני הולך להיות הוריד. אני אעשה את התנועה, מה אתה חושב? אני אעשה ככה.